Here we are going to see about, especially about the Gunn diode. That is very, very important about this, how it is going to work and why it is also called as two-valley diodes. So that all discussion we are going to see, and what is the uniqueness of this, how it is going to obtain the negative resistance. So, okay, that all discussion is going to happen along with what is the various mode of operation in case of Gunn diode, as well as what is the Gunn effect. That all we are going to see. So this is coming under the microwave solid state devices. So when you are going to study about microwave, we are going to be familiar with three different devices. One is the solid state devices, another is the O type, and next is the M type. So these three types of the devices we are going to see in the microwave. So still you didn't subscribe our channel, please subscribe it, share with your friends, like, and write your comment. So this microwave solid state devices are divided into these four components. First one is the avalanche transit time device. So here we have reed diode, impact, trapped, and buried diodes. And in case of transferred electron devices, Gunn diode, LSA diode, indium phosphide diodes, cadmium titanium diodes. So these are the transferred electron devices. Apart from this, we have field effect transistors. You are much familiar with this. JFET, HAM, MESFET, MOSFET, NMOS, PMOS, CMOS, and memories and CCD. All these are coming here, the field effect transistors. And last one is the microwave transistors. Under this, we have microwave BGT, HBT, and tunnel diode. So tunnel diode is also very important. Might you have seen in the lower class. So here we are going to discuss about this transferred electron devices. That is what Gunn diode. About that we are going to see. So before this, we'll see what is the Gunn effect. Okay. So this is Gunn effect diodes. That is another is the gallium arsenides. Gallium arsenide is the compound semiconductors. That is elements are available in the third and fifth columns. Okay. By this, they are getting the gallium arsenides. So this is the example of the compound semiconductors. So it is discovered by the J.B. Gunn. So on his name only, his name is the Gunn effect, and later we are going to see about the Gunn diode. So what he has discovered that there is the periodic fluctuation of the current when it is going to pass through the N type of the gallium arsenide. This was discovered in the 1963. So that fluctuation, later we'll see that how this fluctuation is going to provide the oscillation in case of Gunn diode that we are going to see. So here he came to conclusion about amplification and oscillations of this fluctuation of the current is going to give us due to the negative resistance. So negative resistance means voltage is going to increase, okay, but current is going to decrease. Like here voltage, current. So here if waveform is going to be like this, voltage is increasing but current is decreasing. So that is called as the negative resistance that we'll see. So it is not based upon this junction property. Okay, it is based upon this tunneling phenomena. Due to that, how we are going to have negative resistance. So they have taken the N-type gallium arsenide or N-type indium phosphides. So both show the property of the Gunn effect. So this current oscillation caused by this periodic nucleation and disappearance of the traveling space charge provide the instabilities. Okay. So what is the Gunn effect? So again, we are going to define here. So it was done for the observation for the N-type gallium arsenides, that is the bulk diode. He stated that above some particular critical voltage, not at the normal voltage, some critical voltage, like we have 2000 to 400 volts per centimeters, that is the electric field. So in that situation, this fluctuating is the function of in time. So this current is going to fluctuate, and that is going to be function of the time. So in case of gallium arsenides, so this fluctuation is going to take the form of the periodic oscillation. So due to this periodic oscillation, so that is going to be inversely proportional to the specimen length. What is the construction we are going to take? It is inversely proportional of the length and approximately equal to the transit time of the electrons between the electrodes. Like we have cathode and anodes, how much time it is taking to reach from the cathode to anodes. So that is proportional to the transit time and inversely proportional to the specimen length, what we have considered. Like for example, if you observe here, so here we have cathode, here we have anode, and dimension is 120 micrometer, 100 micrometers, okay? And another dimension we have 75 micrometers. And here we have high field domain. So you see here that velocity is going to be 10 to the power 5 meter per second. So in this high field domain only, this current fluctuation will takes place, and finally it's provide the oscillations. So this carrier is going to drift. So that drift velocity, are you aware of this? Am I right? So this drift velocity is going to occur. So that is going to increase from the zero to the maximum. So when it will be maximum, it depends upon the electric field. So that is going to be vary from the zero to threshold value. So we have seen it is going to be 2000 to 4000 centimeter volt per centimeters. So when it's going to cross that limit, so there we have such type of the situations. So here it is 3000 volts per centimeter is considered. So then drift velocity is going to decrease, okay, and diode adjusts the negative resistance. So here mobility is going to decrease. So drift velocity is going to decrease what after threshold value, that is what 3000 volt per centimeter. Due to that, it's going to get the negative resistance, and this threshold value ETH equal to B upon L. So now finally, we'll see Gunn diode. This is the transferred electron devices. So this is the important questions. Generally, they'll ask you, explain about the Gunn diode and write its mode of operation. So both things we are going to see here. So what is the Gunn diode? It is the passive two-terminal semiconductor devices, and it has only N-doped semiconductors. It doesn't have P-type, only N-doped semiconductor materials, like we have gallium arsenides, radium phosphides, gallium nitride, and all these things. And here, this highly doped, okay, N plus substrate is taken. On this epitaxial layer is ground, so it has three N type of the layers. Later we are going to see that we have N plus on this epitaxial layer is ground. Again, one more layer is ground, and both side is the highly doped, okay, and this is the center part is the normally doped. So that middle layer, if you're going to compare, so other two are the extreme layers are the highly doped, these two, okay. So that structure you can see here. So we have this structure which drawn like look like a gun, bullets, okay. So we have N plus, the highly doped, and this middle one is the normally doped, and both side we have metal contact here as well as here, and it's going to generate more heat. So heat sink is also very important. So this Gunn diode you can see in the lab also for the laboratory experiments you are going to use. So here this is the active layer which is normally doped. That is only important for us here where all oscillation will take place. So this is called as the active layer, and these two are the highly doped. And this is the symbol of this Gunn diode. So you are seeing that these triangles are connected back to back towards that pointed vertex. So when DC voltage being applied here, so that what will happen, that electric field is going to develop across its layer. So especially in case of central active region, so that electric field is being developed. So now initially what's happening, this conduction is going to increase. Why conduction is going to increase? That electrons are going to move from the valence band to the lower value of the conduction band. So we have, like here we have valence band, this is the conduction band. In the conduction band, we have lower valley as well as upper valley. So this is the lower valley, this one is the upper valley, and electrons are moving from here to here, again moving from here to here. So we'll see that how we'll have negative resistance also, that we are going to see. So at higher voltage, the electrons in the lower value of the conduction band is going to move to the higher value. So initially, when voltage is given, so finally that is moving from where? Valence band to conduction band. So that this is the normal behavior. Okay, it is going to the lower value. And further, if you are going to increase the voltage, so it is going to move from the lower value to the higher value. So in higher value, what is happening? So that mobility is going to decrease. So here mobility is going to decrease. So already we have seen about Gunn effect. Okay. So mobility is going to decrease. And here due to that, what will happen here? Current is going to decrease. So it is also due to increase in their effective mass. So effective mass of the electrons are going to increase. Mobility is going to decrease. Due to that, even voltage is going to increase. Current is going to decrease. So due to that, conductivity is going to decrease, and finally flow of current decreases through the diode. So due to this, voltage is increasing, okay, current is decreasing. So due to this, what we have, negative resistance region is there. So here we can see that here in the horizontal axis we have wave number, vertical axis we have electron energy. So here this is from the valence band, electron is going to move to the lower value of the conduction band. Here forbidden energy gap is the 1.43 electron volt. So here mass is 0.068, okay, and mobility is the 8,000 centimeter square volt second, okay, in the lower value. And when it is going to move from the lower valley to upper valley, so this is the gap is here 0.36 volt between this lower valley and upper valley. And in case of upper valley, this having a effective mass is going to increase, that is going to become 1.2. What is here 0.68? 0.068, that becoming 1.2. So it's quietly very large. And that's why mobility is going to decrease. That is only 180 in compared to 8,000 in case of lower valley. So then later you'll see that how we are going to obtain the graph in this format, and this part is going to be the negative resistance. Any doubt is there? You can write in the comments. Okay. If it is useful for you, please try to write. Your interaction, your feedback is important. So here this diode has what? Negative resistance. So initial condition when we are going to increase the voltage, current is also going to increase. So we have this path and it is going to reach to the peak value of the current. So this point is called as the peak current. After that, now mobility is going to decrease, effective mass is going to increase. So here what's happening? In the previous one, it is moving from where? Valence band to lower valley. Now it is moving from the lower valley to upper valley. So here mobility is going to decrease in this due to effective mass is increase. So finally this is going to give us negative resistance. So negative resistance means voltage is increasing but current is decreasing. So previous portion is due to, that is the tunneling current, and this portion is negative resistance. And after that, it has minimum value of the current. That point is called as the valley point. After valley point, again, it is going to work like a normal diode. So this is the maximum operating limits. So this region, if you see that this is same as the normal conventional diode, either you talk about the PN junction diode and all these things. So this VI characteristics is very important. Okay. So what are the limitations? So this is the poor conductors, and Gunn diodes generate the excess heat. So already we have seen that heat sink is required. And at microwave frequencies, this current pulse travels across the active region. So active region is the middle one at a specific voltage. And this pulse reduces the potential gradient and preventing further pulse formation. And again, when new current pulse will be formed, it will be generated only when previous pulse reach to the far end. When it will reach to the far end of the active region, then due to that, potential gradient is going to increase again. So potential gradient is going to increase. So finally, new pulse will be formed. So to vary the oscillation frequency, the thickness of the central active region must be adjusted. So that middle part, that is the normally doped, that should be thickness should adjusted based upon the experiment. So what is the advantage of Gunn diode? It is the cheapest source of microwaves, compact in size, and large bandwidth and high frequency stability. But what is the disadvantage? High turn-on voltage, less efficient, below the 10 gigahertz. So it is going to be operated at high frequencies and poor temperature stability. So we are going to use here heat sinks. What are the various applications? So it is used to generate the microwave frequency, and it's pump the sources in where? In parametric amplifier, okay, and in radar, and it also uses the sensors in the DUR operating systems, and it is source of microwave frequencies in traffic signal controller, and it is the in microwave receiver circuit, radio communications, various military systems, remote variation detectors, tachometers. You are aware of much about tachometers, and pulse Gunn diode generators. Apart from this, we have microelectronics as control equipments, and radar speed guns, and microwave relay data link transmitters, and in continuous wave Doppler radar. So these are the Doppler. Already you are aware of this. Okay, radar is what? Radio detection and ranging. So that is used to detect the targets. Okay. So now, apart from this, if they're asking you about this mode of operation, so that mode of operation we are going to see. So here we have modes of operation, okay, for the Gunn diodes. So you see that in this diagram, basically in the horizontal axis, what is taken? N naught into L. That is the doping into the length, product of doping and the length. So that is given here. That is the centimeter, that is like its area vectors, okay. So when we have doping here and multiplied by the length, that is given in the cm to the square minus 2, so that is cm by c by, that is the centimeter, okay. And here what we have in the vertical axis, we have fl, product of frequency and length, okay. So that is given again here cm per second. So all these like here frequency is what? 1 by time. So length is in centimeters, so time in seconds, so that is centimeter per seconds. And here same way, doping, what is the concentration and what is the, that is the, we'll talk about the volume. So that due to that, we are writing here centimeter to the power minus 2. So here we have 10 to power 11, 10 to power 12, 13, 14. In the vertically, we have 10 to power 6, 7, and 8. So now you see that in different regions. So like if you see, if you're having this product N naught into L in the range of 10 to power 11 to 10 to power 12, and it is FL is below 10 to power 7. So this is having a small signal stability here. And the right side where this Gunn diode is work mostly, where product N naught into L is more than 10 to power 12, and it is it is here around the 10 to power 7. So if you see that here three different modes we have here, like we have quenched domain gun, transit time domain, and delay domain. So this is the part where Gunn diodes are going to work. Again here we have LSA, that is the separate one, and this part having positive resistance. Everything we have to compare with the product of N naught into L and F into L. Here we have lossy dielectrics. So lossy dielectric means it is not perfect dielectric. Here conductivity will not be equal to 0. And here ratio of N naught by F is taken. So that is 2 into power 4. Here it is 2 into 10 to power 5. So in between this we have LSA mode. And here if you see that we have a stable amplification, this portion where it is F into L is more than 10 to power 7 and it is below the 10 to power 12. That is the product of N naught into L. So this diagram only we are going to discuss in detail. So this Gunn oscillation mode. So this Gunn oscillation mode, the product of N naught into L is what? 10 to power 12 per centimeter square, and it is going to lie between 10 to power 14 per centimeter square. So in this range, and here this product of frequency and length is what? About 10 to power 7 centimeter per second. Okay. So in this range, if it is device structures is there, so this region is what? Gunn oscillation mode. So device is unstable because of the cyclic formation of either accumulation of charges at the layers and due to high field domain. So due to accumulation and due to high field domain here, instability is there. So this frequency of oscillation is given as F equal to V by L of. So this is the DOM means domain velocity. LEF means effective length. So like we have seen in case of Gunn effect also. So that specimen size is also important. So this electron dip velocity varies with the electric field. So there are three possible domain modes. In case of Gunn oscillator mode itself, we have three different. First one is what? Transit time domain mode. So here product of FL is around 10 to power 7 centimeter per second. So that you see this diagram is only important what we are going to explain. So this is the transit domain. So here what is the value? 10 to power 7. Okay. So in this domain, same thing we have to discuss. So this electron drift velocity is going to be equal to the sustaining velocity, that is the Vs. So that is going to be Fl equal to 10 to power 7 centimeter per second. And here oscillation period is equal to the transit time, Z not equal to Zt, and efficiency is below 10% because of the current is collected only when domain arrives at the anode. So efficiency is what here? Less. In case of delayed domain mode, what we are seeing that range of FL is what? 10 to power 6 centimeter per second to 10 to power 7. And here E is less than the threshold value, and new domain cannot form until this field rises above this threshold value. So in this, if you compare, T naught is greater than Tt. So Tt is the transition time. So it is also called as inhibited mode, and efficiency is about 20%. In previous one, efficiency was less than 10%. Third one is the quenched domain mode. Here FL is greater than 2 into 10 power 7 centimeter per seconds. So that vertical line you can see. So it is the bias field drops between sustaining field ES during the negative half cycle, and domain collapses before it reaches the anode. It's not going to reach there. So finally, due to this, when biasing field is going to swing back around the threshold value, then new domain is nucleated and process repeats it again. So resonance frequency is the several times this transit time frequency, and efficiency we can obtain here 13%. So what we have seen that in the second one, delayed domain mode, only efficiency is 20%, and previous in transit time 10%, and quench we are getting the 13%. So here it is represented by the help of waveform. So this is the threshold value, this is the ES, and here if you see in case of transit time mode, tau naught equal to tau T. So this is the DC bias here, and you can see the waveform also. Okay, in horizontal axis we have biasing and time here, and vertical axis is the voltage. Where in the delay mode, the time period of this waveform is greater than transition time. So delay occurs, it's reached later stage. Okay, and third one is the quenched mode, where period of this waveform is less than the transition time. That you can see that transition time period is here, but it is shorter than this. And next is we are going to see later about LSA mode, that is the limited space charge accumulation mode. So here what we are seeing that tau naught is smaller than transition time. So that is approximately 3 times of this tau T. Okay, so on the basis of that, different waveforms are here. So this waveform is important to explain the mode of operation of the Gunn diode. So last, this is the limited space charge accumulation, and another one more type we are going to see. So in Gunn oscillation, we have seen 3 sections. This is apart from this limited space. So here FL value is greater than 2 into 10 to the power 7. So that portion we have seen. Okay. So current in this device is proportional to the drift velocity, and efficiency we are able to reach about 20%. And at low frequency, that drift velocity is given as FL, that is 5 into 10 to the power 6 centimeter per second. And ratio already we have seen in the way diagram there, N naught by F equal to 2 into 10 to the power 5, and upper frequency is the FL, that is 5 into 10 to the power 7, and ratio of N naught by F here is the 2 into 10 to the power 4. So between these two range, if you see in the waveform, that is the diagram we have drawn there. Okay, here we have LSA mode. And third one is the stable amplification, that is the small regions where N naught into L is the less than 10 to the power 12 per centimeter square. Okay, it has amplification at the transit time frequency rather than a spontaneous oscillation. So it is having amplification where at transit time, not at a spontaneous. So there are too few carriers. Okay, very less carriers are there for domain formation within the transit time. And here we have summarized all these things. Okay, so here we have time relation, we have doping levels and nature of circuits. So all mode of operation you can understand here with the help of these specifications. So this diagram is previous one is important, and along with this block diagram. Okay, so this is the how they're going to ask. Simply if they're asking about operation of the Gunn diode, so write little bit about the Gunn diode, then discuss about this all this mode of operation. If they're asking only discuss about the VI characteristics and operation, that is working part of the Gunn diode, so then this operation is not required, but at least you can write their name. Okay, any doubt is there, write in the comment box. Like, share, subscribe. Thank you very much.